So the nice thing is, as we talked about before, that the one sample, dependent sample are more or less the same once we sort of get to a certain point. Okay, so a researcher believes that administering Prozac will decrease his anxious patient's level of perceived stress. That may seem odd. You're like, wait, so Prozac is usually prescribed for depression. And the idea is that, I imagine because depression and anxiety are comorbid, they often appear together, that if you actually treat the depression, and likely reduce the anxiety as well. I'm just making it up, but so to evaluate this hypothesis, he takes 5 of his anxious patients and evaluates their level of perceived stress using a psychometric scale, which is called Scale X, whatever, where high scores reflect more perceived stress. He then proceeds to, he prescribes them a standard dosage of Prozac and has them take it for like 6 months. At the end of 6 months, he administers the scale again. So test the researcher's hypothesis. Alpha equals 0.05, assuming the scale is normally distributed in the population, because we only have 5 patients, so it doesn't quite meet the central limit theorem requirement of having sort of 20 or more people in the sample. So the only way really to do this would be we'd have to assume that anxiety is normally distributed in the population. Right? Those are the 2 ways you can get a normally distributed sampling distribution. Either the population is normal, or the sample has enough people, which is like 20 or more. All right, so what do we know? Research believes that administering Prozac will decrease anxious patients. Okay, so we're looking, as the word decreased in there, so it's likely going to be a directional test, one-tailed test. To evaluate this, he gives them a test beforehand. So there's a before test, and then there's an after test. So the fact it's talking about a before and after test gives you some clue that this is a dependent sample, sort of pre-post, repeated measures, whatever term you like, type of test. So there's 6 months in between before and after, and none of the other information is really given. There's no population value, nothing really given to you that will indicate a one sample or something test. We're looking at before and after, and the numbers are given here. So you got the before and after and the difference, before after difference, right? We got the mean before, mean after. We got the standard deviations sort of before and after, and then we got the standard deviation of the differences. This is one of those cases where it really illustrates how much sort of variability is sort of reduced here, where the standard deviation for these scores is actually 11.5. The standard deviation for the after scores is 10.953. But look, standard deviations of the differences is way smaller, right? So there's a huge reduction in the noise and random variability by looking at the different scores we talked about during the lectures that sort of illustrated really well in this example, all right? All right, so there's not a whole lot for us, in terms of, figuring out. We know it's a dependent samples test. We know there's pre and post. We know all this stuff. So we know a couple things just to sort of keep things straight. We know that the n equals 5. There are 5 participants because we're looking at the 5 different scores. The mean that we're interested in is that mean of the different scores equals 5. The standard deviation of the different scores equals 3.536, and that is essentially everything we need to do the dependent samples test. And it's saying alpha 0.05. If it said nothing, we would assume that anyway. So we're ready to go and start applying this. We know pretty much everything. We can do the 7 steps. All right, so steps 1 and 2, state our null, state our alternative. So again, think about the alternative. What is it this researcher is trying to do? Again, Prozac will decrease, prescribes them, test Richard's hypothesis. The only other place doesn't say really anything else except for decrease. Decrease seems to be here. It thinks Prozac will decrease anxiety. So we got to be thinking about that. So it means that the mean of the differences I think the mean of differences, okay, if there's no change, if giving these clients, these patients, Prozac does nothing, I would expect their level of anxiety before and after to be the same. So I'm assuming that the differences, again, depending on how I do it, so I'm doing before minus after, which means I would expect, right? So the mean of the differences, we can say this is like before minus after, right? It's going to be greater than 0. I should have more symptoms beforehand, right? Less symptoms after. So if I take more minus less, I should have a positive number. So expect something larger than 0. So if that's true, then the null is going to be the opposite, where the differences of before minus after are going to be less than or equal to 0. If there's no change, I expect them to be equal to 0. If giving them Prozac somehow makes them worse, then I expect I should have more symptoms afterwards. When I subtract them, I get a negative number. That would actually also be bad. Okay, so this is my alternative. I'm thinking that if I take before minus after, I should have positive numbers. This should be actually reducing the anxious scores, anxiety scores on the after test. So it makes sense. I like it. Okay. So 3, all right, it states right there that alpha equals 0.05, but if it didn't, I could assume it. Step 4 kind of tests this. As soon as you start seeing that there's, before and after scores or something like that, that it's 2 different samples, but they're the same people, so they're dependent samples, and we're subtracting and getting different scores. As soon as you know all that stuff, it's fairly clear it's a dependent samples test. Okay, dependent samples t-test. So 5, we now need to figure out the critical value, right? So my t critical with, now I know it looks like it, you may think, well, there's 5 before and 5 after, so that's 10 minus 1 is 9 or something. This is the only thing that, in terms of the actual data, the only data that really matters is the differences. We're no longer interested in before and after, because we're going to be doing analysis on the different scores. So there's only 5 different scores. So the degrees of freedom here are going to be 5 minus 1 equals 4 degrees of freedom. I need my alpha equal to 0.05. And it needs to be one-tailed, because that's what my hypothesis is stating, right? It's a one-tailed test. Okay, so let's figure out what that t-critical looks like. Go back to my t-table. And now I'm interested in one-tailed, 0.05 again, right? We're not doing 0.01 like we did on the last example. 0.05 one-tailed, go down to 4. All right, pretty easy. 0.05 down to 4 degrees of freedom, 2.1318. 2.1318. 2.1318. So now we got to think about it. Okay, so think in terms of direction. It's greater than, so I'm interested over here. 2.1318. So I'm interested in the right hand side, the positive side of the distribution as a one-tailed test. So this does remain as a positive. So we could say if my t observed is greater than 2.1318. Now you notice I'm not doing absolute value. I'm not putting a negative number. It's positive. It's only a positive 2.1318. If that happens, I'm going to reject the null. Reject the null hypothesis. All right. I'm going to erase this for a second. So let's do step 6. Step 6 is the, where the most of the work goes in. Step 6 is my t observed equals the mean of my difference scores. Really, minus 0, because that's what we're talking about here in terms of the null. I'm sorry, with that a little too high. It's like interfering with the words there. Equals the mean of the difference scores minus 0. And again, 0 because that's what we're talking about in terms of the null. Over, I need a standard error of the mean of those differences. So to get this, it's going to be the standard deviation of the differences over the square root of n. Alright, so this is going to be pretty straightforward, I hope. So let's go down here. So that means t observed equals, so what's my mean sub d? Well, let's set it up there, it's 5. Alright, so I got 5 minus 0, it's just 5, over my standard deviation is this 3.536 divided by, I only have 5 subjects, so the square root of 5. So that means 5 over, let's take 3.536 over the square root of 5. 3.536 divided by the square root of 5 equals 1.581. So this is 1.581. 5 divided by 1.581 equals 3.163. And this is that's our t observed. It's 3.163. Actually, make sure this is actually, okay. So our t observed is 3.163. So now I can go to step 7 and say, since 3.163 is greater than, it's positive, I'm staying positive, 2.1318, I'm going to reject the null. So remember, the null states that so nothing happened, that either they're going to stay the same or the symptoms are going to get worse. Or given our sample and what we found there, them taking Prozac for 6 months or whatever, that we're going to reject that idea. It actually seems like there's some evidence that their symptoms were reduced, that 5 points of reduction on average in their symptoms was in fact a significant change. Right? This change is not likely to have occurred by chance alone. And even though it doesn't state it here, what if I wanted to know something like the effect size and or the confidence interval? So the effect size here would be, so let's say I wanted to do a Cohen's d. So again, we're looking at the mean before minus the mean after over the standard deviation of before, of the pre, right? So this is going to be 27 minus 22 over 1.511 equals 5 over 1.511. So whatever that is, whatever 5 divided by 11.511, 5 divided by 11.511 equals 0.43. And if you're asked about, the size of it or something like that, well, again, we know the 0.2 is small, 0.5 is medium, and 0.8 is large. Well, this falls somewhere here. It's a small effect. It's moving up towards medium, but not quite there, so it's still a relatively small effect. So even though it's a significant effect, right, it's a relatively small change relative to the variability that people have in their pre-treatment anxiety. All right, so that's how you look at the effect size. What about the confidence interval? All right, so for the confidence interval, the 95% confidence interval for this is going to be the same thing. I just really need the mean of the differences. I'm going to add and subtract from that my T critical at 0.05 and 2 tailed. I know it's 0.05 because it's asking for the 95% interval. Okay. I'm going to take that, I'm going to multiply that by our standard error. The standard error of the mean of that difference score. I'm going to add and subtract that. Okay, so we did it as a one-tailed test before, so I don't have the T critical. So I got to look it up. Let's look up the T critical with 4 degrees of freedom. The degrees of freedom doesn't change. So it's still 0.05, but I need it to be two-tailed. So down here, two-tailed test, 0.05. You come down to here, it's 2.7765 is my 4 degrees of freedom, 0.05 two-tailed value, 2.7765. So this ends up being 2.7765 times, now of course I already forgot, let me switch it, you can't see me. So that T critical is 2.7765 times, and of course I already forgot my standard error, but I can figure it out pretty fast. If my, this is my, I need my S sub m of the differences. So that's going to be S over the square root of n. So my S is 3.536, 3.536 over the square root of 5 people. So let's do that again. So I already forgot. I erased it. 3.536 divided by the square root of 5 equals 1. So this whole thing, my S sub m sub d equals 1.581. Like that. Okay. So I'm going to plug that in here. 1.581. And I need to multiply those out. So 2.7765 times 1.581 equals, so I'm going to be adding and subtracting from this 4.39. Oh, technically it's 4.3896. So, yeah, 3.390, okay? So I'm going to take my 5, which is my mean of the differences. It's a horrible 5. I don't know what the heck that was. So let's take my mean of my differences, which is 5. And I know that because it's right here. Mean of my differences is 5, okay? So 5 plus or minus this right here means I'm going to get my confidence interval, my 95% confidence interval for this particular example, is going to be 5 minus that. So 5 minus 4.39 equals 0.61, which is less than or equal to the true mean of the different scores. Let's say mu sub d, which is less than or equal to the 5 plus 4.39, which is 9.39. Okay, so that's my 95% confidence interval, somewhere between 0.61 and 9.39. So again, if you do this 100 times, I expect the differences between these groups to fall somewhere in between here, 95 of those 100 times. And this sort of tells me what the real population for different scores looks like for this particular sample. That wasn't asked in here, but I figured it might be. It might be something, part of a practice problem or a test question where you're asked to do a problem and then figure out the effect size, figure out the confidence interval. So I want to make sure and at least give you an example of that.